Welcome to another Achieving Science video. This video is going to look at giant covalent structures. So what is a giant covalent structure? Well, a giant covalent structure is similar to that of a giant ionic structure, the difference being that a giant covalent structure contains no ions. Within the giant covalent structure, there are very strong covalent bonds between all of the atoms. These strong bonds are very important because they mean that these covalent structures have high boiling and melting points. This is because lots of energy is required to break these very strong bonds. Another property is that giant covalent structures do not conduct electricity, as they do not have any ions. This is with the exception of graphite, which is able to conduct electricity due to it having one delocalized electron. Giant covalent structures are usually insoluble in water, i.e. they do not dissolve in water. Throughout this video we're going to look at some different examples of giant covalent structures, but for instance they contain or include examples like diamond and silica, otherwise known as silicon dioxide. We need to be able to look at the different properties and the reasons why they have different properties. So let's have a closer look at them all. First of all, let us begin with diamond, a very important structure. Diamond is in fact made of pure carbon. If we look at its chemical structure, we can see that it is made up of 4 carbon atoms covalently joined to each other in this pattern as shown on the screen. It forms a very rigid structure. Diamond is in fact the hardest natural material with a very high boiling point and melting point. It doesn't conduct electricity. Due to its hardness, it is able to be used for things like drill tips. The second giant covalent structure to look at is silica, silicon dioxide. This is what sand is made of. Each grain of sand is actual fact one giant structure. When melted with sodium carbonate and limestone, it is able to form glass. The third structure to look at then is graphite. It's not lead in our pencils, instead it is graphite. It is made up of carbon atoms forming 3 covalent bonds, forming hexagonal rings. We'll have a look at these in a minute. These layers are able to slide over each other, which allows us to see the graphite being left on our piece of paper as we write with it. This is because there is no covalent bond between the layers. Graphite has a high melting point, and remember this is able to conduct electricity and thermal energy due to the presence of one delocalized electron, as in actual fact carbon is able to form 4 bonds and not just the 3 as graphite does. Let's now have a look at this in a bit closer detail, because we said that it forms a hexagonal structure and layers. These layers can be shown in this diagram here. And it is important to remember that these layers are able to slide over each other. And because these carbon atoms are forming 3 bonds, you've got to remember that it does have that free delocalized electron that allows it to conduct electricity and thermal energy. Graphene then is in particular a special product. It is a single layer of graphite. As it is a single layer of graphite, it is only 1 atom in thickness. Next, let's look at fullerenes. These are molecules of carbon atoms with hollow shapes. They are based on hexagonal rings of carbon atoms, and these rings may contain between 5 or 7 carbon atoms. They can be used for drug delivery, as lubricants and as catalysts. Finally, let's look at a particular structure called nanotubes. Nanotubes are cylindrical fullerenes. They have high tensile strength, high electrical conductivity, and high thermal conductivity. They're used for things like reinforcing materials such as tennis rackets.